In this video, we'll be looking at ammonia and ammonium compounds. Now, here are some few things you need to know about ammonia. The first thing is that ammonia is the only alkaline gas. Ammonia is the only alkaline gas, and then we test for ammonia using damp red litmus paper. So, test, use damp red litmus paper. So the red litmus paper turns blue when it comes in contact with ammonia gas because ammonia gas is basic. Now you also need to remember that we make ammonia using the Haber process. Now if you don't remember the Haber process, we have a video on it on the channel. You can check the playlist for the Haber process. Now, in the Haber process, we combine nitrogen and hydrogen to make ammonia. So you have N2 gas. This is the Haber process. Now, the next thing you need to know is how to draw the dot and cross diagram of ammonia. Now, in doing so, you need to draw the outermost shell of nitrogen. So let's say this is nitrogen. Remember, it is the central atom. So I have nitrogen. Nitrogen has 5 electrons in its outermost shell. So the next thing I need to do is to draw the hydrogens. Now I'm going to have 3 hydrogens bonded to the nitrogen. Good. So for the nitrogen, there are 5 electrons in the outermost shell. So it's going to share 1 with each of these hydrogens. It is going to share 1 of the electrons with each of these 3 hydrogens. So hydrogen, so I'm using white dots to represent the outermost electrons of nitrogen. Now, that means that I'm going to have 2 more on the nitrogen. So this is a lone pair of electron. Now the electrons from the hydrogens, I'm using cross for that. So at the end of the day, the outermost shell of nitrogen is fully filled with 8 electrons, and we say that the outermost shell of the hydrogens are also 2 electrons. So this is the purpose of covalent bonding. Now, essentially, you need to remember that nitrogen here is sp3 hybridized. sp3 hybridized. Now, you must remember that for an sp3 hybridized orbital, you should have a tetrahedral geometry, but that is not the exact case that we see in the case of ammonia. Now, in ammonia, because we have a lone pair on the nitrogen, we are going to have a trigonal pyramidal. So I have the three hydrogens here, and I have the lone pair on the nitrogen. Now what happens is that instead of the regular tetrahedral geometry where the bond angle is going to be 109.5, now the lone pair is going to repel the bonded pairs in a way that the, the bond angle is reduced to about 107 degree. So 107 degree, making it appear to be pyramidal. So if you picture this, this is like a trigonal base, and then the nitrogen is pointing up. So we describe this as trigonal pyramidal. So trigonal pyramidal. That is the geometry we see in ammonia. Now, so in the reactivity of ammonia, what happens is that the lone pair on the nitrogen is donated to a proton. So what that means is that ammonia behaves as a base because we have the nitrogen here with a lone pair, and then we have three hydrogens bonded to it. So what happens is if we add an acid, the acid is going to release H plus. Now in this process, this lone pair is donated to the proton, which is H plus, and that validates Lewis' definition of an acid as electron pair acceptor, or that validates Bronsted-Lowry's definition of a base as a proton acceptor. So if that happens, we have nitrogen now having 4 bonds. In that case, I'm going to put this in a square bracket with a positive charge. Now this charge is spread evenly across the molecule. This time, this we call it ammonium. And this is ammonia. Now the geometry we see here is tetrahedral. Unlike the ammonia, which is trigonal pyramidal, the ammonium ion is tetrahedral because all the bond lengths are the same. So because of this, when we put an ammonium ion in water, we have it dissociating to give an H plus. So in a case where we have ammonia itself in water, there is an equilibrium that is established. So you have ammonia, NH3, plus water, and then you're going to be having ammonium, NH4 plus, and OH minus. So this is aqueous, liquid, aqueous, and aqueous. So ammonia is the base. Water here is acting as an acid because it is the proton donor. So in the words of Bronsted Lowry, this is going to be your conjugate acid. And this is your conjugate base. Good. So ammonia is acting as a base because it is accepting the proton, and water is acting as an acid because it is donating the proton, which means that water is a stronger acid compared to ammonia. Now, in this reaction, just correct this. This is equilibrium. This is an equilibrium reaction, so you have a double arrow. Now, the equilibrium lies far to the left, which means that we only have a small amount of the hydroxide in the solution. Now, this makes ammonia to be a weak base because if it were to be sodium hydroxide, you are going to have a complete dissociation. So it is a strong base, but in this equilibrium reaction, you have more of the ammonia in a higher concentration compared to the hydroxide anion. Now, the final thing I want you to take note of is that when you heat an ammonium salt with a base, it produces ammonia gas. Now let's look at an example of that. If I have an ammonium salt NaH4 Cl, so this is ammonium chloride. Now, if I heat this with calcium hydroxide, this is solid, this is solid as well. If I heat these two, I'm going to form subproducts. So I have calcium chloride and I'm going to have water H2O, and the last product is going to be ammonia. Now to balance this, I need to put 2 here, and for ammonia, I'm going to put 2, and water is also going to be 2. So this is the way we prepare ammonia gas in the lab. Now to test for the ammonia, let's test for this ammonia. Remember what we do, we use damp red litmus paper, and it's going to turn blue. Now, for this reason, since we have water in there, if we are preparing this gas and we need to dry it, we use calcium oxide to dry the gas. So drying agent in this reaction is calcium oxide. So this is what you need to know about ammonia and ammonia compounds. See you in the next video.